Hello everyone, my name is Robail Yasrab and I am working as a postdoc researcher at Department of Engineering, University of Oxford. The topic I'm going to present today is anatomy-aware contrastive learning for fetal ultrasound interpretation tasks. Learning from limited label data is a fundamental problem in machine learning, which is crucial for medical imaging analysis because annotation of medical images is time-consuming and expensive. Domain gap between natural images and medical images causes inevitable performance bottleneck. Self-supervised learning is recently getting more attention because it doesn't require manual labels and learning meaningful representations. In particular, contrastive learning has become a mainstream as shown in the right, where models is trained to pull together each instance and its augmented views. Meanwhile, push away from those other instances in embedded space. However, directly applying contrastive learning in context of medical images may lead to false negatives. Some negative samples having high similarity with the anchor image are pushed away. There are some recent approaches that improve the data sampling in contrastive learning by constraining selection of positive pairs only from the sample subject video, as they assume that visual representation from sample subject share similar semantic meanings. To address the aforementioned limitations, we explore the following question. Is the domain-specific anatomy information helpful in learning better representation for medical data? And we investigated this question by firstly presenting an AWCL architecture where anatomy-aware means the anatomy information is incorporated to augment the positive-negative pair sampling. In this way, previous false negatives and false positives problem can be rectified. Moreover, we consider both coarse and fine-grained anatomy category for data sampling and empirically investigate their effects on anatomy-aware contrastive learning architecture. For evaluation, we assess the generalization and transferability of trained architecture on three downstream tasks for first trimester and second trimester data. In terms of prior work for exploring the representation of learning for fetal ultrasound are mainly from our group. However, our work focuses on learning general image representations without requiring additional data and modalities from domain of interest. Data used in this study was a part of PULSE project, which consists of full-length routine for second trimester fetal ultrasound videos. We considered a subset of entire ultrasound data for the proposed pre-training, which contains more than 2 million image frames from 534 second trimester ultrasound scans. In this dataset, there are more than 15,000 frames labeled with 13 fine-grained anatomy categories and background, as shown on the right. In addition, more than 69,000 frames labeled with 12 coarse-grained anatomy categories and others. The figure on the left shows the proposed architecture. The assumption for such design is that images sampled within the same anatomy category should have the similar appearance based on the clinical perspective. We used SIM-CLR architecture as a baseline. Incorporating additional samples belong to the same anatomy class will help to boost the performance of training. We utilized available anatomy information from upsample dataset and designed the AWCL architecture as followed by the paper objectives. However, A into I is not always achievable in sampling process, as we don't have labels for the training samples. Therefore, we formulated AWCL as an alternative optimization combining the both conventional and anatomy-aware contrastive objectives. Moreover, we considered both coarse and fine-grained anatomical categories for the proposed AWCL framework. And we compare their effects on transferability of visual representation. This diagram shows the design the main difference between the both methods, and whether the sagittal plane of the spine is considered into the positive pairs. For an anatomical structure of different views of visual appearance, we observe AWCL with coarse-grained anatomy information tend to minimize the interclass differences by pulling together all the instances of same anatomy. In contrast, AWCL with fine-grained anatomy information tend to preserve the interclass differences by pushing away images with different visual appearances despite the same anatomy. Then we evaluated the learned models via transfer learning. Table 1 shows the details of downstream datasets and imaging tasks for fine-tuning. There are 2 tasks for the first trimester and 1 task for the second trimester. This table also shows the partitions of different classes and images and samples. For the performance evaluation, we first show the quantitative comparison of fine-tuning performance on 3 evaluated downstream tasks. The results are shown in Table 2. We compare our AWCL trained models with random initialization, ImageNet pre-trained models, and other benchmark architectures. For the task 1, the results we can see that contrastive pre-training approach underperformed the supervised pre-training, which has the same for the semantic supervision as in task. For task 2 and task 3, we evaluated how pre-trained models generalize against distribution shifts with the data from first trimester ultrasound scans. For the results, we can see that AWCL fine-grained in both tasks achieves the best performance among all the compared results. In particular, AWCL fine-grained outperforms ImageNet by 5% and 13% in F1 scores and MIOU respectively. Besides that, AWCL course outperform SimCLR, CLPI by large margins in task 2 and task 3. Here we show some quantitative results on classification and segmentation tasks. This again demonstrates the effectiveness of our proposed approach and suggests that this approach can learn task features and better generalizations to tasks from the different domains. Analysis of anatomy ratio on AWCL tasks. We investigated how varying anatomy ratios impact the AWCL architecture. Note that higher anatomy ratios represent the higher number of samples, same or different from ultrasound scans, belonging to the same anatomy category or including from the positive pairs of contrastive learning. We incorporated the anatomy information with 4 different ratios, 10%, 13%, 50%, and 18%, to train AWCL fine-grained models on the pre-trained datasets respectively. The graph shows that by increasing the anatomy ratio, the performance of the respective trained models have increased. That shows that more anatomy information is fed to the architecture, the performance will improve, vice versa. Conclusion. We presented a new anatomy-aware contrastive learning approach for fetal ultrasound tasks. The proposed approach able to leverage on more positive samples from same or different ultrasound videos with same anatomy category and align well with anatomical characteristics of ultrasound videos. The proposed AWCL architecture with fine-grained anatomy information preserves the intra-class differences with more effective than its counterpart. The proposed approach is advantageous to provide useful transfer representation for various downstream clinical tasks, especially in cross-domain generalization. In coming future, we are intended to release the code and train model so the other people can use the similar architecture for ultrasound pre-training tasks. That's all from my side. Thank you.